Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about operators in Verilog. So we are going to see what are all the type of operators we have in this Verilog. So basically these operators are classified into unary operators, binary operators and ternary operators. So these operators are classified into binary operators, unary operators and ternary operators. Unary operators are the operators which have only one operand. Unary operators are the operators which are only having only one operand. Whereas in the case of binary operators, we have two operands. And in the case of ternary operator, we have three operands. So these are the different type of operators which we are going to discuss in our sessions. So we have unary operators, binary operators and ternary operators. So what do you mean by unary operators? Let us briefly analyze what is your unary operators. So if you have A plus B, so this is your operands. So these are your operands. So these are your basically operands and this is our operator and this is our operator. So this is a binary operator since we are having two operands. Okay, example for your unary operator is not of A and example for your binary operator is A and B and example for your ternary operator is conditional operator A question mark B colon Z. Here you have three operands. Okay, this we will discuss in detail. What is this? Okay, so let us start our discussion with our logical operators first. So we are going to discuss about first the logical operators. So logical operators, we have three different logical operators. First one is AND operator, logical AND. The symbol for logical AND is double ampersand. And we have logical OR. Okay, the symbol for logical OR is this one. And we have logical NOT. Okay, so this is logical NOT. Now, let us discuss one by one. And one more important point in the logical operators is the output of this logical operation will be either 0 or either 1 or either unknown. That's it. The output for this particular logical OR operation will be either 0 or either 1 or either unknown. For example, if we have a value, let's say if we declare any variable as reg a is equal to 5 and sorry, if we declare any variable as reg 2 down to 0, 7 and reg 1 down to 0, 5, 1 down to 0, 3. Okay, so if we perform the logical operation reg 2 down to 0 a is equal to 7 and reg 1 down to 0 b is equal to 3, and if we perform logical AND operation, for example, that is let's say your output is reg y. Okay, so y is equal to logical AND operation of a and b. So the resultant, what the compiler is going to do is, so number either than 0 will be considered as true value. So if you have this numbers 0, 1, 2, 3, so this will be considered as logical low and any other value which is other than 0 will be considered as logical high. Logical high or 1. So this will be considered as logical 1 and this will also be considered as logical 1 and your output will be simply equal to y will be equal to 1. Okay, let's see one example of this logical AND operation or operation everything. So here I am using my EDA tool. So let me declare a module logical operations. So let me declare some variables here 3 down 2 down 0 a b and c, and let me declare some output variables so that I can store my values. So within an initial beginning block, we will discuss what is this initial beginning block, everything. So the value of A which we are declaring is 5, and the value of B is 110, and the value of C is unknown. Let's say it is unknown. Okay. Now if we perform the logical AND operation, let's see what is the result we are getting. So logical AND operation of A and B, and let us display this. The value of A is percentage B, comma, sorry, Y. We are going to display the value of Y. So basically, the compiler, this is going to consider this whole value as logical 1. This will be considered as logical 1, and this also will be considered as logical 1. So logical 1 and with logical 1, the logical operation between 1 and 1 will be equal to simply 1. Okay. So let me end this and end module. Yes. So what you're getting, so the value of output Y is nothing but 1. Now let's say uh, if you are performing AND operation between your A and C. So the value of C is unknown and the value of A is 5. Okay. So this will be considered as X. Okay. Let me save this and run this. Yes. So you will get simply Y value that is equal to unknown. Now let us try to perform the logical OR operation. Okay. So let's say X is equal to A logical OR with B. Okay, and let us try to display the value of X. Okay, let me save this. So the value of X is percentage B comma X. Okay, I'm performing logical OR operation between A and B. Okay, so 1 OR with 1 is simply 1. Logical OR operation between 1 and 1 is simply 1. So that only we are going to get. Let me show you. Yes, so the logical OR operation is nothing but 1. And let's say if you want to perform the logical OR operation between A and C, then save this and run this. Again, you're going to get the value of X is equal to 1. So here you are going to get your value of X is equal to 1. So what is the reason? We were expecting the value to be given as unknown, but we are getting it to be 1. What is the reason for this? We were performing so let us try to see the reason why we are getting like this. So we have considered A value to be 5, that is nothing but 101, and B value to be tick binary X, sorry, C value to be tick binary X. Okay, and what we were considering, our value should be equal to unknown, that is X output X is equal to A logical OR with C. We were expecting unknown, but what is getting? So let us try to analyze. So this will be nothing but 101. If you perform OR operation, if you perform OR operation, if this particular value, this is simply considered as logical 1, right? So this value is considered as logical 1, and this second value is unknown. The second value is unknown, considered as unknown. Okay, but what is logical OR operation between 1 and X? So you can consider this X either as 0, then also you will get output as 1, and if you consider this particular X as 1, then also you are going to get output as 1. So that's why we are getting our output to be 1. So the logical OR operation between these two values, that's why we are getting our output to be 1. That is the reason. And let us perform the last operation. Let us perform the logical NOT operation. So Z is equal to NOT of A. Okay. Let us try to perform the logical NOT operation on this particular thing. So the value of Z which we are getting is simply 0. Okay. And let us perform the logical NOT operation on this C, that is unknown has been stored, right? So let us perform. So we are getting unknown. The value of Z is unknown. So these are your logical operators. Coming up next, we have bitwise operators. Let us try to analyze what is the bitwise operators. So bitwise operators are the operators. This we are going to perform all the operations bit by bit. Okay, between all the bits we are going to perform. Unlike your logical operations, we are going to perform the operations on each and every bit. Okay, so we have bitwise AND operator, single ampersand, and bitwise OR operator. This is your bitwise OR operation symbol, and XOR operation, bitwise XOR, and we have negation operator. So this is bitwise negation, and if you have this exclamatory mark, this is logical not operation. Okay, difference between this is logical not operation and this is bitwise not operation. And you have XNOR operation, or also you can write this one. Okay, both are same. So let us try to analyze your results. So let's say if your A value is 5, if you perform and your, let's say, B value is let's say 3 tick binary 110. Okay, and if you perform, let's say your output is X, which is a 3-bit variable. So X nothing but A bitwise and with B. Okay, so your result 5 will be converted to 101, and B is nothing but 110. 101 with 110, your output should be equal to 1 and with 0 is 0, 0, and 1 and with 1 is 1. So your output should be 100. That will cross verify. Okay, and you have, let's say, Y is equal to A or B, bitwise OR. Okay, that is 101 or with 110. You should get 1 or with 0 is 1, 1, 1. You should get 311. That will verify. And you have, let's say, uh, Z, which is nothing but not of A, that should be equal to 0, 1, 0. That also we are going to verify. And let's say your output X is equal to uh, XOR of A. Okay, this we are going to verify. Uh, Output X is equal to XOR of A. So what should be your result? Your result should be XOR operation between each and every bit. 1 XOR with 0, XOR with 1. That is nothing but 1 XOR with 0 is 1, XOR with 1 is 1. Your output should be this. Let us try to verify this. So let me remove this. So module bitwise operations reg 2 down to 0 A B C X Y Z. Let us declare them now. So within our initial block, what I'm going to do is I'm going to assign my value of A is equal to 5, B is equal to 3 tick binary 110, and let's say the value of C is unknown, tick binary X. Okay, so what are the operations which we have seen? And operation. Let us verify X is equal to bitwise AND of A and B, and let us display the value of X, or display the value of X is percentage %B comma X. Okay, and let us perform bitwise OR operation between A and B. So, and let us display this. Let me copy this and paste it over here. The value of Y is percentage %B. Okay, and we have XOR operation also we have done, right? So let us store it here in the value Z. So Z is equal to XOR of A. Okay, the process I have shown, right? So let me display the value of Z also. So the value of Z is percentage %B comma Z. Okay, now let us try to display everything in and in module. Let me save this and let me run. So the value of X we are getting is 1000, which is matching with our results, and the value of Y is 111, which is also matching with our results, The value of z which we are getting is, sorry, here the result, it is not 1, it is 0. 1 XOR with 0 is 1, 1 XOR with 1 is 0. So that's why we are getting 000. Yes. Now if we want to perform XNOR operation, just what we can do, let us declare one more variable as output variable as m, so that we can perform some more operations, comma m comma n comma p. Okay, so let's say your m is nothing but negation of a. Okay, your m is nothing but negation of a. Let us display the value of m is percentage b comma m, and let us display the value of n, which is nothing but XNOR operation of your a. Okay, so how to represent this XNOR operation is this symbol you can use. Okay, so let us display this dollar display the value of n is percentage b comma n. Okay, let us display everything again. So the value of n is 001, m is 010. Okay, so this is how you are going to use your bitwise operators. Now let us try to discuss about another type of operators which we have, shift operators. Let us try to discuss this type of operators, shift operators. So what are these shift operators? Let us try to discuss. So we have two type of shift operators. One is right shift operator. So this is a right shift operation, and we have left shift operator. So this is left shift operation. So we have two type of shift operators. One is right shift operators, and another is left shift operator. And after performing these operations, the resultant width will be same. Okay, there is no change in the width of the resultant. And again, these shift operators are again classified into two types. One is logical shift operation, and another is arithmetic shift operation. So one is logical shift operation and another is arithmetic shift operation. Let us try to analyze what is meant by logical shift operation, what is meant by arithmetic shift operation. For example, let's say a variable a which is storing the value 4-tick binary 0110. Okay, so this, if we want to perform right shift operation, okay, 0110 on this, if we want to perform it, first let us try to discuss logical right shift. Okay, logical right shift operation. Let us see the result of your logical right shift operation. So this bit will be transferred here, and this will be transferred here, and this will, we will get here, this we will get here. Okay, so the operation will be nothing but 0011. This is your resultant of your logical right shift operation, simple right shift operation. Okay, next, coming to logical left shift operation, the resultant, if you have 0110, then this will be shifted to left side. Okay, this will come to MSB bit, and this will come here, and this will come over here, and one more 0 will be appended on the left hand side, and this will be removed. Okay, so your resultant will be 1100. So this is the resultant of your logical left shift operation. Now let us try to see how to use this syntax. In this particular case, we are shifting the bits by only one bit position. Okay, so if we, let's say if we have a number 0110, and if we want to perform the shift operation for the two times, then the resultant will be, after performing the first shift, the resultant is 0 will be appended out, and followed by 110. Okay, this will be shifted over here, this will be shifted over here, and this will be shifted over here, and we will have one more 0 here. Okay, so this is the resultant of first shift. Okay, this is first shift, and after performing second shift, your resultant is nothing but this will be appended out. Okay, and you have in MSB1 you have 0 followed by one more 0, and one more 0 will be inserted here. Okay, so this is your resultant of second shift operation, arithmetic left shift. Now if you want to write it in the Verilog, so how you are going to write it? Let's say you are storing this particular bit inside a variable a, so you are going to simply write a left shift of, sorry, we are performing left shift, right? So a left shift of how many bits we are, how many shifts we are performing? Two shifts. So we are going to write, so this is left shift by, and if you are only performing left shift operation only once, okay, then you are going to write a left shift of 1. This is left shift by 1. And this is normal logical shift operation. So the symbols, this and this, these two symbols are for logical shift operations. These are your symbols of your logical shift operations. And if you have this symbols, these are your arithmetic shift operations. This is the difference between your arithmetic shift and logical shift. We will discuss exactly the difference. And if you want to see it in the coding part, now let's say the value of what we will take, the value of, let's say, y. Okay, let us consider the variable y and let's perform arithmetic shift and logical shift. Let us declare one more variable, reg 2 down to 0, ls left shift operation and reg right shift operation. Okay, ls and rs. So ls, which is equal to a right left shift by a left shift by 1 bit position, and let's say, let us display that dollar display. The value of ls is percentage b comma ls. And let us also perform the right shift operation, which is nothing but a right shift of 1 bit position. And let, sorry, not r, not a, we are performing on y. Okay, we are going to perform it on y. And let us display it. Okay, this is the resultant of your right shift operation. And yeah, so let's see what is our results. So our y is nothing but the value of y is 111. The value of y is 111. So if you are performing left shift operation, the resultant should be 110. And if you are performing right shift, the resultant should be 011. Okay, this is right shift operation. RS value should be 1011 and LS value should be 110. Let us see what we are getting. Let me save this. Wait, let me first save this. So the value of ls is nothing but 110 we are getting, and the value of rs is nothing but 011. Okay, and if you try to perform yeah, so this is left shift operations and right shift operations. The logical left shift and right shift are normal shifting operations. Now let us try to discuss your uh, arithmetic shift operations. Arithmetic shift operations uh, will retain the MSB if the operand is a signed variable. Okay, so let's say, let us declare a variable reg 2 down to, okay, not reg signed 2 down to 0 a, which is nothing but let's say 3 tick binary 111. So the value of this is nothing but -2 because it is a signed variable. The 1 is nothing but the sign, and the remaining part is nothing but your value. Okay, so let us perform the arithmetic. Now let me declare a signed variable, signed underscore variable, and let me assign it a value of 3 tick binary 111. And let me perform the arithmetic right shift on this particular signed variable, and let me display the value of this signed variable, the arithmetic right shift on this particular signed variable. Let me save this. And let me run this. Let's see what is the value we are getting. So it is 111 only. So normally, if you are performing, so normally if you are having 111, and if you are performing logical right shift, what you should get? You should get 011. But see here, if you are performing arithmetic right shift, the MSB bit is restored. So you are getting one only, and remaining is getting shifted. That's it. So this is the resultant. This is the difference between your arithmetic right shift and left shift. And let us see your left shift also. So on this particular signed variable only, let us perform the left shift operation. ALS, which is equal to signed underscore variable of left shift, arithmetic left shift, and let me display the value of ALS. So here we are getting 110. So if we have the value 111, if we perform normal left shift operation, then also we will get 0, 1, 1. And if we perform arithmetic left shift also, we are going to get the same value. Okay. Yes. So this is how. And let's say if you have 101, then let's see what is your arithmetic left shift operation. If you have the value 101, so if you are having 101, and let me comment this right shift operation. So if you are having 101, then what is happening in the case of normal shift operation? You will get 0, 1, and 0. This is happening in the normal logical left shift operation. But in the case of arithmetic left shift operation, the MSB is restored. It is not getting changed, and the remaining bits are getting shifted. So this will be shifted over here one, and one more 0 will be added. So this is arithmetic left shift, and this is normal logical left shift. So this is the difference between your arithmetic left shift operation and normal left shift. Now let us see your another type of operators, which are known as concatenation operators. Concatenation operators. So this basically concatenation operators are used to join together, join the bits and the resultant. So basically, these concatenation operators are used for joining together of bits resulting from two or more expressions. So let us say, for example, if your value of A is equal to 3 tick binary 110, and if your value of B is equal to 3 tick binary 111, and if you want to group this two bits, okay, we can have one more variable y, and we can use this particular concatenation operator, and we can write simply A comma B. So the value of y will be equal to 110111. So you're basically grouping these two bits. You're basically concatenating both. You can also write the value y concatenation of A comma 3 tick binary 000. You can also combine the variables as well as the bits. So the value of y will be equal to 110000. This also you can do. And let's say if we want to concatenate this two bits and this two bits, okay, so the syntax what we can write is y is equal to A of 2 down to 1 comma B of 2 down to 1. That is y value will be equal to 1111. So you can basically slice it and you can combine it, no issue. Okay. And let's say if you want to replicate this value of A for 2 times, then the syntax which you are going to follow is y is equal to concatenation of 2 concatenation of A. So this number will give uh, how many times your variable should be replicated. Okay, this is replication number. So the value of y will be equal to simply 110110. Okay, so let us see this with some examples. So which example we will take? Let's say let's take the values of x and y. Okay, so let me declare some more variables. Reg 5 down to 0 concatenation operation. Okay, so cnoc underscore op is equal to cnoc underscore op, which is equal to concatenation of x and y. Okay, and let us curly braces we should use, and let us display the value of x and this one, the value of cnoc underscore op is percentage b comma cnoc underscore op. Let us display this. So cnoc is 110111. Sorry, 100 111. Okay. And let's say if you want to replicate it for two times, so cnoc underscore op, if you want to replicate the x value for two times, you can use this one. Okay, let me save this and let me copy this display statement and display it over here. So the value which we are getting is 100 and let's say if you want to slice it, so what you can do is conoc underscore op, which is equal to concatenation of x of, let's say if you want 2 down to 1, okay, that is 2 bits, and 1 bit is 0, 2 bits, and remaining 2 bits are 0, so total 4 bits, and still we need 2 number of bits, right? So let's say it is y of 1 down to 0. Okay, like this we can do the concatenation operator. Let me save this and run this. So we are getting 100. Sorry, let me display that value. So we are getting 100,011. Okay, the value of x is 10. We are basically slicing now. So we are basically slicing x of 2 down to 1. So 10 is copied and we are adding two tick binary 0 zeros. So we are adding two zeros. Okay, two zeros has been appended, and we are taking again slice of 2 1. Okay, y of 1 down to 0. So we have taken 1 and 1. Okay, that is we are getting. So this is how we can slice and we can use it in the concatenation operator. And we have another type of operators which are relational operators. So let's consider them. So let us first declare some variables: reg greater than, less than, equal to, less than, and greater than, equal to. Okay, so let us perform the relational operators. So greater than, let's say gt is equal to x greater than y. If it is greater than, you will get the display as 1, you will get the value as 1, or else you will get the value of gt to be 0. Okay, the value of gt is percentage %b comma gt. Let's see this. 0, because x is not greater than y, so we are getting 0. Simple operators. And let's say less than, x less than y. Let us see the lt also, and we can keep lt here. And one more thing, let's compare it with the unknown a and c. Let's compare a and c. So we are getting simply unknown. Okay. So this is greater than, less than, greater than, equal to, and less than, equal to. Now we have another type of operators which are known as case equality operators. So now we have another type of operators which are known as equality operators. So let us try to see what is this equality operators. So these equality operators are again divided into two types. One is logical equality and another is case equality. Okay. Let us try to understand them with the example only. So let's say we have a reg, uh, already m is declared now. So let us take the value of m to be equal to 3 tick binary x01, and n is equal to 3 tick binary 1, uh, 10x. Okay, and let me declare the variables reg equal to and case equal to. Okay, and reg not equal to and case not equal to. Okay. Case equal to and case not equal to, let us see. So equal to, which is nothing but m. In the normal equal to operation we have only two equal symbols, and in the case equal to case equality operation we have three equal to symbols. Okay, and neq, which is nothing but m not equal to n, and case not equal to m exclamatory double equal to m. Okay, so let us display this everything. Let us see what is the results we are getting. So this is equal to. Okay, let me copy this. Okay, so this is normal neq, and this is case equal to, and this is case not equal to. So this is neq, and this is case equal to and case not equal to. Okay, let me save this and run this. So normal equal to, if you see carefully, we are getting unknown, because normal equal to equality operators cannot compare your unknown values. But and in the case of not equal to also we are getting unknown. But in the case of case equality, they can compare the unknown values also. Okay, they are basically performing the equality operation on the unknown values also. Okay, so that's why we are getting 0, and in the case of case not equality we are getting 1. So let's say if we have x over here, and let's see the case equality and case not equality, what are your outputs. So then also you are getting CEQ 0 and CNEQ as 1. Now let's change this particular bit, make it to X, and let's save this and run this. Yes. So now you are getting CEQ as 1 and CNEQ as 0. So this is your equality operators. Now let us discuss about one more operators, which are known as conditional operators. So what are these conditional operators? Let us see, let us try to understand these conditional operators. These are also known as ternary operators, because we have three operands, right? So these conditional operators, we are going to check for the conditional expression, question mark, true expression, or false expression. So if this condition has been satisfied, then the output will be equal to true expression, or if the condition is not satisfied, then the output will be equal to false expression. This is the meaning of this particular conditional operator. Okay. So here we should write our output. Output is nothing but if the conditional, this particular expression has been satisfied, then the output will be equal to this particular true expression, or else the output will be equal to false expression. This is similar to your if else loop. That's it. Okay. Let us try to have some variables and let us see. Let's say, where is your variable? Let us take the CEQ. Okay, and let us take the CEQ, and what else you have as outputs. Let us take this P. Okay, so this output P will be equal to, let's say, what is the condition? Let's check is CEQ is equal to 1, then P value should be equal to X, or else question mark X, or else it should be equal to Y. So what we're basically checking, if the CQ will is equal to 1, then P value will be should be equal to X, or P value should be equal to Y. Let's see the value what we are getting, and let me run this. Let me display this first. Dollar display the value of P is percentage B comma P. So here we should get the value of P, that is nothing but X, that is nothing but let's say 100 we should get. Yeah, 100 we are getting. That's it. So if you write the reverse, CQ equal to 0, if this condition has been satisfied, then the P value will be X, or the value of P will be equal to Y. Okay, let me run this. See. So the value of P is nothing but Y. Y value, if you see over here, the Y value is nothing but 111. So that's all about this particular operators in Verilog. And we have some more operators like arithmetic operators, which are simple plus, minus, multiplication, division, modulus. So we are not going to discuss that since these are very basic operators. Yes. So that's all about this particular video. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you.